So welcome to the seminar of the Sony Astani Department of Civil and Environmental Engineering. Today we are very honored to have Michelle Povinelli to give us a talk. And Michelle is an assistant professor of electrical engineering and presently holds the Wise Junior Gabilan Chair of USC. She is a recipient of an NSF Career Award and also a recipient of an Army Young Investigator Award. Congratulations, Michelle. She received a BA from the University of Chicago, MPhil from the University of Cambridge in the UK, not on the East Coast, where she studied as a Churchill Scholar. She's also, she has received her PhD from MIT, the Massachusetts Institute of Technology, in physics. So all our degrees are in physics. She completed her postdoctoral research in the electrical engineering department at Stanford University and was selected as one of 5 national recipients of a L'Oreal for Women in Science postdoctoral fellowships. She has co-authors over 25 refereed journals, articles, and holds 2 US patents. So it's really a great privilege today for us to have Michelle to give us a talk. Let us welcome Michelle. Michelle. So we're going to give you the... Okay.
Yep, okay. All right. Thank you for coming. This talk will be perhaps a little bit different. I know everyone here is a civil engineer, and this is not a civil engineering talk, so let me tell you a little bit about why I'm here. A few months ago, I met Sammy and Roger, and we started talking together about different ways in which some of the structures which I study in the area of nanophotonics might be used for civil engineering and sensing applications. Now, we haven't started that work yet, so you won't be hearing about that today. You'll be hearing about, in general, what the bit. I'll start by introducing the types of things we study in the area of nanophotonics. I'll give a little bit of an idea about how this can be related to strain sensors for civil engineering applications based on things people have done in the literature. Then I'm going to tell you about the projects that my students are working on. And that section, you should feel free, both in that section and throughout the talk, to stop me whenever you want, because it may get a bit more technical, and I'm hoping it'll be interesting enough to carry you along, even if it's not directly relevant to civil engineering. And so by the end of the talk, you'll get a picture of some specific projects so that you see how the methods that I use in my work are actually applied to specific problems. Okay, so to start out, I'll just point out the title. The 2 specific projects I'll talk about later in the talk are going to be moving objects with the forces of light and using nanostructured materials to improve solar cell performance. But before I get to those topics, I want to start out by introducing from a higher level what it is that we do in my group. So you just heard a bit about my background. Point out that I'm coming from physics background and now working in electrical engineering. So I'm interested in connecting some of the basic science of light and light interaction with nanostructured materials to different applications. The main ones that I work on are applications to optical communications. Now we're working on solar energy. And we're starting to look towards other application areas, such as biology, and potentially through collaborations here through civil engineering or strain sensing. But what you'll see here is still very much at this interface of basic science, just starting to figure out how this new science applies to applications. My background as a PhD student was all in the theory and simulation area. And so what we did in my PhD group and what we continue to do in my group is large-scale electromagnetic simulations, where we take very detailed structures. I'll talk more about what these do later. But we take different nanostructures where these circles may represent, say, holes in a material like silicon, and we do accurate calculations of the electromagnetic fields within these structures in order to be able to predict what happens in experiment. Like perhaps some of you, we use the HPCC supercomputer here, which has over 1,800 processors, and so allows fast and accurate simulations of realistic 3D structures. We use these simulations in order to understand optical physics and design devices which manipulate light on the nanoscale. As a postdoc, I got increasingly interested in actually making these devices, not just calculating them. And so I've also gotten into device fabrication and testing. We use the semiconductor processing techniques, similar techniques as you would use to make circuits, here in the USC cleanroom, and then characterize devices in our lab. And in this work, we also work with people here on the USC campus. So we are collaborating with John O'Brien's group, who has a lot of expertise, Dan Dapkus's group, and others in the device fabrication area so that we can implement our designs and test them. Okay. So when I say that the main theme of my group is interaction of light with micro and nanostructures, these are some examples of the structures I'm interested in. The examples shown here show you a range of different geometries, and they also reflect a range of different ways of making them. This one on the upper left, this is a result from a group at MIT that make particular type of structured fibers. So this is the wall of the fiber. Fiber looks like this. And if you zoom in on the wall, you see it has this layered structure. The function of this is to act like a mirror and to keep the light in the center of the fiber. And a neat thing about these structures is that they've been able to make novel waveguides that are really good for high-power carbon dioxide lasers, which can be used for endoscopic surgery. So here is one example of how you can introduce microstructure to control light. These turned out to offer a lot of advantages over the previous waveguides, which were made out of metal, not very flexible, and couldn't be used to access, for example, the lungs. Over on the right is an example of a two-dimensionally periodic structure, and this is made lithographically, so in a clean room, and it's made out of gallium arsenide, so on a semiconductor chip. This has particular waveguiding or circuit-like properties, except that we're guiding light instead of electrons. And this was from a collaborator at MIT. Down here, this shows an example of a 3D structure that people have made. And here, it's three-dimensionally periodic, composed of these little spheres, and is made by self-assembly. So you let the spheres settle out in solution, and they assemble these structures. I want to point out the dimensions that we typically work with here. Visible wavelength light has a wavelength of 380 to 750 nanometers. The light that goes through fiber optic cables carries information on the internet is a wavelength of 1.55 microns. And a lot of the work that I do is in this range, considering applications into fiber optic networks. And for example, carbon dioxide lasers, such as for the application up here, have a wavelength about 10 microns. So this whole wavelength range can be of interest. And what enables this whole field is that you can actually make all these different structures that have fine structure on the scale of the wavelength or smaller. So because of this added control that's been developed in the last 10 or 20 years, we can start to say, okay, these are great, but what other structures should we make that would be interesting and have interesting applications? Let's go and design some and then make them and figure out how to use them in different contexts. So one class of materials which I study are called photonic crystals. These are periodic media, and they're not naturally occurring. You make them, like the examples you just saw. You take a piece of material and you structure it, either in 1, 2, or 3D periodicity. The key feature of these photonic crystals is that they have what's called a band gap. What the band gap means is that there are certain frequencies or wavelengths of light which can't propagate through the material. So if you came in from the outside, you would just reflect off. These structures act like mirrors. Or you can think of them as insulators. They don't let the light in for certain wavelengths. So perfect structures act like mirrors, and this has been used in different applications to make high reflectivity coatings, to make so-called perfect mirrors that will reflect any polarization of light from any angle. And that's what you do if you have, a nice crystal. However, you can also take your perfect crystal and then deliberately ruin the periodicity So for example, if you have a 2D periodic system of, for example, silicon rods in air, this won't let any light propagate in the plane. But if you go and you take one of the rods out, you can create a solution of the electromagnetic equation so that light just gets localized here right near that smaller rod. And the light can't get out because it acts like a mirror, so the light gets confined within this very small scale that's about the same as the wavelength of light itself. So in real units, this is maybe a micron by a micron. So we can trap light in these tiny spaces. You can also guide light along very small, narrow channels, again, say on a scale of a micron, by removing a whole row of rods. So here the light can go here, but it can't get out because these are acting like mirrors. Okay. Another class of devices in this same general field are small microcavities and waveguides, but not based on photonic crystals, based on the principle of index guiding. So this here is a fiber. You've probably heard fibers, fiber optic cables. And because its refractive index and is a little bit higher than the surroundings, the light tends to stick in here. So you can make waveguides this way. Just guide the light down a slightly higher index material. It is possible for people to then couple light into different types of microcavities. This one's a sphere. The light goes and runs around the edges of the sphere without escaping. So this is from Kerry Vahalla's group at Caltech. They've also made these microtoroid shapes where the light goes around here. And another version of this general idea is micro rings. Here, this is silicon. The light comes up here, and then it can couple into the ring. I want to point out that two people who make these structures here at USC, Andrea Armani, who came a year ago and is from the Valhalla group, works extensively with these as biosensors and other sensing applications. And Dan Dafkis's group, for example, also makes micro-ring structures. These can be made, both of these, in our clean room. So these are some of the ingredients. You saw something about what a photonic crystal is and something about what these microcavities are, either in photonic crystals or in these index-guided structures. And we're now going to talk about some different examples of how you combine those elements to get interesting optical devices. One of the ultimate goals of this general field is that we want to be able to take standard optical elements. This is a standard optical table. On this table, you might have waveguides, things that split beams in two, recombine them, filter out certain wavelengths, maybe lasers to generate light, change the polarization. We want to be able to take all of these different standard optical functionalities and shrink them down to chips so that you'd have something that looks like a circuit, only instead you're guiding light around and performing different processes on that light to process information, so carry information, transmit, do optical signal processing. This is one vision, and it's the one most suited to insertion in fiber optic networks to do information processing at network nodes, as well as to make connections between processors and computers. Since processor speeds are currently flattening out, one of the nearest short-term applications for this technology is to connect multiple processors using small integrated waveguides to get faster computing. However, there are other applications. Once you start making really small devices, you can also use them for other things. So for example, one of the areas that we had been talking about and that led to my coming and telling you about this here today is connections to strain and displacement sensing. So here's the cartoon version of what's going on. Say you have one of these materials and it has some special microstructure that you design and you figure out is optimal. If it's a photonic crystal, remember I told you it acts like a mirror for certain frequencies? This is a cartoon plot of that. If you plot the reflection off the surface as a function of frequency, you have this high reflection band. If something happens to your material, so if you stretch the material or compress it, this whole spectrum comes from the structure. So if the structure changes, your spectral feature changes and shift. So one sensing mechanism, then, you look for spectral shifts from your material. So you send light at it, measure the reflection as a function of frequency, and you see shifts. This is a bulk sensor. You just take one of those crystals. It has a high reflection region. Down here, this is a cartoon of a resonant sensor. So if you take a microcavity element, like the ones you saw both here and here, all of these microcavities have a similar feature that if you look at their reflection as a function of frequency, they have a resonance in the reflection. Similarly, if something happens to your resonator, so if your actual resonator changes shape, the particular frequency of the light that can travel around and be supported by that resonator shifts, and so you get a resonant shift. And this then is a second sensing mechanism, similar.
Typically, what is the frequency of resonance?
Mm-hmm. So you can design these. A lot of work has been done at 1.5 because of fiber optics. You can also design them to work in the visible. If you go to visible wavelengths, the wavelength's a little shorter, so your features are a little smaller, and you have to try to make the devices a little bit better.
1.5, which unit?
Microns? Yeah. So anywhere from red, blue up to infrared. Now, you can do things like this in other ranges as well. So for example, there's a whole area where people do terahertz photonic crystals, and their terahertz wavelengths are longer. And so they make photonic crystals that are bigger. People have also done work in millimeter. So when the idea of photonic band gaps was first proposed, people didn't have such nice microfabrication facilities to run downstairs and use right away. It took some time to get into it. And so people made huge ones where the holes were millimeters big, and then they used microwave waves to do the tests and show that there were band gaps, this range of frequencies where the light reflects off. So it can, in principle, apply to whatever length scale you want if you have a way of making that structure. Another side note, there's also a field of acoustic band gaps. So it's not just light. You can imagine a similar thing with acoustic waves. If you have now materials with different rigidities and you pattern them periodically, you can make a mirror for acoustic waves where acoustic waves can't penetrate. And people have also designed those types of structures. So that's something that may resonate, perhaps for some, more than light. I mean sound familiar, not be resonant. Okay, so one example of this from the literature is from this paper in Nature Materials. And this was using these photonic crystals as pressure sensors. So in this case, they took a 3D material and applied compression. So as you go this way, it's a little hard to see, but you see these shrink a little. They put some pressure on it, and as they increase the pressure on it, they measure reflection as a function of wavelength. I'm sorry, that's a little fuzzy. And you see the peak shifting over. So if you compress, this says 276 nanometer lattice constant here, and then this went down to 188. So kind of significant shift got you that far, but you could observe the wavelength shift. And this is measured in reflection using a spectrometer. In that same paper, they had a nifty demonstration. Up top here, this is how they actually made it. They took some spheres, you self-assemble them so they stack up on their own. Then you infiltrate a background material, peel it off, and then your peeled off thing eventually gets put on the substrate you're testing. And in the end, there's air here in the voids. So they did this kind of cool experiment. They took a thumb. You take this, and you shine light, say, from the back, and you put your thumb down on the top. And as you put the thumb down and you press down, you see these color changes, and they correspond to the ridges of your thumb. So anywhere that was more pressure. As you apply pressure, you shift the band gap. A shifting band gap visually looks like a change in color. Changes the reflectance, the wavelength for which the reflectance is optimum, and so it shows up as a change in color. So in this paper, they were calling this color fingerprints. So here then is one example of how you can think about pressure sensing based on these optical techniques. Other experiments have been done where people have used different structures. This is one example. You can use a photonic crystal. You can also use some sort of resonant element And then as you stretch it, its resonance changes, and you can do sensing. And this has been applied in a number of different contexts, though not so much with strain. Okay, so to give you an idea of the methods that we use in my group, we do a lot of simulation. And all of our simulation methods are based on solving Maxwell's equations, which are here just for reference. We have a few different methods we use, but one that we use quite a bit because it's very all-purpose general method is the finite difference time domain method. And the way that that works is that you start with some initial condition on your fields. Fields here are the electric field and the magnetic field, E and H. And then D and B are related to them by the material constants. So you start with initial values of the field. You take whatever structure you're interested in. Say you're interested in rods, shown in yellow in air. You would split the structure up into a discrete grid. We only keep track of values on the discrete grid. And then all of our derivatives turn into finite differences. So once you turn these derivatives into finite differences, you can derive an update equation. And provided that you start with the initial condition, you can just step through to update the fields at each step. This method is somewhat slow. It's time intensive. It's full vectorial, so we're treating all the fields as vectors. You have to store both E and H at every point on the grid, so it's somewhat memory intensive. But the upside is that it parallelizes really easily. So schematically that's shown here. If you have a bigger structure, lots of rods in air, you just split it up. And you take each domain and you assign it to a different processor. And if anyone here does parallel computing, you know that the big issue with parallelizing codes is the communication cost versus the computation cost. There's very little communication here because Maxwell's equations, as long as they're all, they're local. So the only thing you have to worry about is derivatives, where you're taking a derivative right at a boundary. That would involve values on either side. So right on the boundaries, you have to communicate, but otherwise you don't. And so computers step forward in time, handle their own domain, and there you go. So this is almost a linear speedup, nearly linear speedup when you parallelize.
You take advantage of standard libraries?
Yes. So we use a few different codes. There was a code that was developed in my old group at MIT, and that's now open access. So the guy who developed that put it out for free. And I use that code a lot because that's what I used when I worked with him. But there are other codes that are commercial. The open access code relies on a whole bunch of libraries. So it uses BLAS and LAPACK. And actually, my coworker wrote FFTW, which is this yeah. So the guy who wrote this package also wrote FFTW, which is now used by MATLAB. So this is very cool. No credit to me. I'm just saying Stephen Johnson is a great guy. And we use that. We also use some commercial code. So when we do problems that involve metals, there are some technical issues where doing FDTD in metals requires a slightly different approach, and then we've been using a commercial code. We also write smaller codes around these codes to process the results, or if we need a new feature that's not in them, we might write a code.
But open source does communication?
Yeah, so this uses MPI. That code is parallelized using MPI to do the parallelization, and that's pretty standard message passing library. There also relies on LAPACK and BLAS as linear algebra libraries. Other methods that we use, I'm not particularly tied to any method. I'm more interested in the physics and the applications. So if the method works, we use it. So there are also frequency domain methods, which are eigenmode solvers. The FDTD method, you start with an initial condition and then you go forward. Eigenmode solvers, you're saying what are all the possible solutions of Maxwell's equations and what frequencies do they have. There are also what are called transfer matrix methods, where if you want a structure and you want to figure out the transmission, you start out with some input light and then you figure out how it transfers through the structure. There are also some perturbative theories, which are called coupled mode theories. These are perturbative theories where either you have well-defined eigenmodes that are slowly changing in space or slowly changing in time. And in some previous work, part of the work I was doing was looking at how you formulate these coupled mode theories for waveguides where you're changing in space. but this is in many cases is useful. We'll often do full simulations to try to do the full 3D realistic behavior, but then come up with some simplified coupled mode theory to explain more heuristically what's happening and then use that for design. Numerics is great, but of course you have to test each case and see what it does. So these can be very useful in guiding that process. Okay, so we also do fabrication of devices. This is two examples of structures that I made showing two different types of silicon waveguides. These are both silicon waveguides, and here these are etched holes. What do they do? This one on the left, light comes through here. It can get stopped by this region. It'll tunnel through to the center and then tunnel out. But that tunneling only happens for a certain wavelength, so this acts as a filter. I didn't make the structure up. This has been studied before. It's just an example to show you fabrication capability. This was something that I was working on as a PhD student. We were looking at taking waveguides. This is a waveguide in the center, and adding a photonic crystal around it to try to reduce scattering loss. And the idea here is that if light's going through here, if it wants to scatter, that scattering process would actually be prohibited by the fact that you had a photonic crystal outside. And now in my lab, we're setting up testing apparatus to test transmission through waveguides and be able to characterize the finished devices. Okay. So I'm now going to switch to the more specific part of the presentation and talk about two of the recent projects my students have been working on. Let me pause for a minute and see if you have any general questions before I move on, anything that's occurred to people so far.
When you were talking about the thumbprint pressure sensor, do you have any method of scaling? Because as you push on it, it does a light shift. There's a reflectivity shift in wavelength. Can you scale it so that a larger force then has that same? So go from like 1 psi to 1,000 psi?
Yeah, so depending what you made it out of, I believe that in that paper they were backfilling with a kind of flexible polymer. If you made such a thing out of something stiffer, then it would take a lot more force. Now, you'd have to come up with a fabrication. You have to come up with the right fabrication process to be able to backfill with something else. But at least in principle, if you make something stiffer but not brittle, then you can adjust what range of pressures you could sense.
You talked about solving all of your equations in terms of Maxwell's equations, which implies to me that there's no sort of quantum mechanical effects that you're really dealing with here.
That's true.
Is there ever situations where those effects do come into play?
So in the problems that I talked about here, most of the work that I have done has been purely classical E&M. However, there are some interesting application areas of photonic crystals and related devices to quantum optics. One area of study is relationship to quantum communication. In quantum communication, you need to generate single photons on demand, and then you take those photons and you send them around somewhere. So there is a group, for example, Jelena Vukovic's group at Stanford, who focuses on using photonic crystals with quantum dots in them to generate single photons on demand. And in that kind of area, then you get more into the quantum optics. And you actually need, in some cases, you need the quantum mechanical description of light. Here we do not. So for something like sensing or the applications I'll talk about here, it is purely classical. So in a way, the equations are kind of boring. Maxwell's equations are linear. You can get accurate solutions. You don't have to spend a lot of time developing fancier solution methods. If you do nonlinear optical phenomena, like changing one color to another, then you have to worry about nonlinearities. But for linear problems, in a way, the equations are kind of boring. They're solvable, but the good side of that is that things match experiment really well. So it's not a question of a theory to explain an experiment. It's really more you design a device, and your design is going to work up to effects that you didn't happen to think of, like, okay, actually the structure didn't come out to exactly the structure you wanted because there was fabrication error. Anything else? Okay, I'm going to change the order here, so bear with me as I go past. I'll come back to these. Okay. So what I want to tell you about next is a recent project that my student is working on, and that's modeling of nanowire solar cells. So the general question that we're interested in is, given that people are able to make materials with a very high level of control over structure on the 10 to 100 nanometer scale, can we use that control over structure to get more efficient solar cells for next generation designs? And this has been proposed by several groups. There was a proposal for nanowire cells from, among others, the Atwater group at Caltech. And some of the advantages, these could be made more flexible than other solid materials. They can be made or fabricated on a variety of substrates. So you can make these structures on glass or foil or plastic, possibly get conformal coatings. And they might potentially have better certain electro-optical advantages over standard cells. However, the experiments that people have done to measure efficiencies so far are terrible, very low, way worse than any currently existing solar cells. So my interest here was in trying to figure out, okay, measured efficiencies are bad. That involves a number of different effects. The light comes in, the light has to generate electron-hole pairs, and then shown here in a color, that's a junction between a p region and an n region. That electron and hole have to be turned into a current. So there are a few different steps there, but we're going to focus now just on the optical absorption, the light coming in and generating electron-hole pairs, and try to figure out how that's related to the structure. So we'll study a model that looks like this. We're considering these nanowires where, like the proposals, they are lined vertically, and they form a regular array. And actually, the absorption properties of these arrays has been quite limited. We found one previous paper from the literature, which was from a group at MIT. And they modeled certain absorption properties here, but they found if you use a structure like this, you do way worse than if you just didn't have any structure at all. So just use a thin film with the same height, and you'll have a higher absorption. Nanostructure doesn't help you. So we read that paper, and we thought that was pretty interesting, but we noticed actually that the one thing that they hadn't varied when they did their study was the lattice constant. In other words, lattice constant shown here, it's the separation between wires. And so my students started looking at what happens if you also vary this lattice constant parameter. So here, I mentioned a number of different methods that we use. For this particular problem, the transfer matrix method is convenient because if you're modeling the response of silicon across the entire solar spectrum, it's a very wide frequency range. The properties in the material change a lot. We call that, so in particular, the dielectric constant's dispersive. It changes with frequency. And this is also a good method when you have absorptive materials. So shown here, this is just the refractive index of silicon across the relevant range for the solar spectrum. We're looking at the range from 300 to 1,000 nanometers, or an energy that's something like 1.5 to 4 eV. This is the dielectric constant, shown over here in blue. This is the absorption. Absorption goes down across this range. So both vary as a function of frequency. And then this shows the solar spectrum. So this is the irradiance as a function of energy. And you see that it peaks here at about 2.2 eV, or alternately about 650 nanometers. So we took our structure and we calculated transmission, reflection, and absorption as a function of frequency, and calculated a number I'll call the absorption efficiency, which is a measure of how well this structure does across the whole solar range. So the absorption efficiency then is given in terms of an integral over the wavelength-dependent absorption, and it's weighted by the solar spectrum I. This corresponds to an upper limit on how well your cell can do. Remember, I said there are a lot of different effects. You have to absorb the light, convert it to carriers, and then collect them. This is an upper limit, assuming that every photon produces one electron-hole pair, and they all make it. They're all collected. So this is an upper bound on our structure. What we did then was we calculated results as you took here. This is very light gray on this slide. This is a rod, and this is the unit cell. Here the rod gets bigger and the unit cell does as well, so we're scaling the whole thing up. So we increased the lattice constant while keeping this filling ratio constant. Filling ratio constant's the area of your rod over the area of your cell. And the results are shown down here. So this is the absorptance as a function of energy. And the black line is what happens if you just had a film. Forget the nanostructure. It's given here. And then these are the results for nanowires as you increase the lattice constant. So you see down here for the 100 nanometer lattice constant, you do worse down here, and then you do better than the thin film up here. Turns out that if you take the integral, overall it's worse. As you increase the lattice constant, though, the whole curve shifts over to where for the green case, you're really doing significantly better than the thin film. If we go even further, something else interesting happens. If you make your wires quite a bit bigger, so 500 nanometers big, here again, this red line is repeated just to give you the reference. For the very big lattice constant, you get a large shift over, and you also get these resonant peaks here. These peaks that you see in the spectrum are actually a known behavior for photonic crystals. So after all, our rods are basically a photonic crystal. It's a 2D periodic structure. And there's certain modes that you can excite that have been studied that give you resonant peaks and extra enhancement. So each of these peaks gives you extra enhancement in the spectrum. And here's what happens when we calculate the ultimate efficiency as a function of lattice constant. Remember, all the previous studies were down here at 100. As we increase the lattice constant, then for a given filling ratio, so let's take the black line, that's 0.2. With an increase in lattice constant, you just do better and better. This is the thin film efficiency for comparison. So you can see already we have a whole number of structures that are better than a thin film. And if you increase the filling ratio and optimize that filling ratio, you can see that we actually do better, not just than a solid thin film, but you do better than a thin film with an anti-reflection coating, which is shown here. And so we can get considerable absorption increases. Oh, this is now published. That's wrong. OK. So this is my student's work that just came out. Chenshi is a PhD student in electrical engineering. And it's kind of neat, non-intuitive result, saying take a thing that's porous. It's a bunch of wires. It's not solid. It actually absorbs more than a solid film. And intuitively, the reason for this is that because this reflects less off the top surface, you can actually do better. You get more light in, and then you get more absorption. So that was the point shown here. What we're working on next, that was silicon nanowires. The highest efficiency solar cells now on the market are triple junction solar cells, and they're made out of compound semiconductors. These are semiconductors. We have one group from group 3 of the periodic table and one from group 5, like gallium arsenide. And nanowires, so we're going to be looking at 3.5 nanowires and questions like, if you could grow anything, what type of structures would give you optimal absorption? We are also investigating this general field of plasmonics. There has been previous work suggesting that in many cases, when you add small metal particles to the top of your thin film solar cells, you can get more light into the film and higher absorption. We're looking at this in the context of nanowires. We have collaborators here at USC. So in our group, we're focusing, for this problem, we're focusing on the modeling side. The groups that are making and growing nanowires, and part of the New Energy Frontier Research Center, which is led by Dan Dapkus. Both the Dapkus group and the Zhao group can grow silicon and 3.5 nanowires in different compositions. And we're working with them as well as John O'Brien in this area.
Michelle, I'm just curious about the effect of the lens. You talked about the spacing of the
Yes.
nanowires, but what is the effect of the lens, or the aspect
Yeah.
ratio of your cells?
So length is also important, and this conclusion that it's better than a thin film will probably not apply over all lengths. And my student is now trying to map out that dependence. The key physical feature is that you have some, for these thin film structures, the problem that we're trying to overcome, one is the reflection. The second one is that the thin films are so short that not all the light gets absorbed. It would actually take a longer length to absorb reasonable fraction of the light in the range where you have low absorption. So this structure is kind of a way of getting more absorption within a short thickness. If you went really long, you wouldn't necessarily need that.
You're trapping, right?
Yeah, there's a trapping effect in the layer.
Optimum effect of trapping, otherwise it doesn't get to the bottom of the order. It's not converted. I don't know. I'm trying to understand how this thing works.
Right, so if you just had a semi-infinite layer, very thick, then you just absorb as you go along, and it depends on the absorption length, and that varies with frequency. With these ones, you can bounce off the bottom and back and forth, so you have an optical trapping effect within this cavity that helps increase, but the amount of that increase compared to, yes, the increase that you get from that effect will have some length dependence, which we are working on mapping out.
So the peaks in your frequency function, I guess, get that close continuity to the simple function.
Yes.
As the length of the fibers gets longer.
Yes, so these come from what are called guided modes of the nanowire structure. They're modes that are, you have a high, they're localized to the film. And if you go off angle, if you come in off angle, then they're actually propagating in the film. And as you make it longer and longer, the density of modes increases, and so you get more narrowly spaced peaks. Then they start to merge, and then it should get smoother.
But how come you have those same things?
Oh, this one?
Yeah.
So these are different, interestingly. These are Fabry-Perot reflections. So in the thin film, you have this off the surface. And in this case, similar but different. It's a different
So as it gets deeper, the two converge.
So this one comes from,
As it gets deeper, you have fewer, or it also gets
oh,
right?
I don't think it converges to that, but yeah, these would merge together. As it gets thicker, this mode density, they get more closely spaced, and if they get closely spaced enough, they should just smooth out.
But the bottom line here, I just see you're doubling the efficiency, am I right?
Oh,
I mean,
okay,
you're
yeah,
doubling,
not quite, but it's not bad.
Just shy of 30,
14 to 23.
Yeah.
Okay, and this is just the optical part. So of course, we have to worry about carrier collection, and this is a practical issue. So anytime you use rough structures like this, you have the possibility of unwanted surface recombination on all of your structures. And so in this plot, this is taken from, not ours, this is taken from our paper. I'm afraid I don't have the reference here, but things like surface passivation to make sure that you don't have electronic defect modes on the surface, which give you electrons and holes recombining without giving you current. These are issues, but this gives the upper bound. Okay, so, I have probably 5 minutes. Okay. 10 minutes, okay. I'm gonna go back now. Yeah, here we go. Okay, a second main area that we're studying is applications of optomechanical motion to these kinds of photonic devices I described. So here we're talking about using light to push on things, make them move, and change how the light travels through the optical circuit. So in PhD work that I did back in 2005, I wrote a paper which was proposing that you could use the force of light on objects to reposition these small waveguides. So your light comes in, and this light actually generates a force between your polarized waveguides. Light polarizes these objects, and they want to attract. As a side note, there's also a repulsive force. Depending how you put the light in, you can get attraction or repulsion. So they'll deform. You hold the ends fixed. These will deform. And more light, turn the light up, it'll deform more. So this was a theory proposal. And then since that time, I was very excited because there's a group at Yale who went and did exactly that experiment. So now it's been done. When I first started thinking about this, I thought, okay, this effect definitely exists, but I don't know if it's big enough to actually move things an observable amount. And now, in fact, it's true. It is observable. So there are experimental demonstrations both from the Tang group at Yale and from the Lipson group at Cornell. Here, this is a waveguide. It couples to a substrate, and the optical force makes it move. Here they took, instead of straight waveguides, they used two waveguides, like two rings like this, and they see the attractive and repulsive forces. There are also related experiments in the Painter group, which has been pushed this area forward from Caltech, and a group in Belgium. With this motivation then, seeing that this actually can work, to give you a sense of the scale, this is about 30 microns. These are a few hundred nanometers by a few hundred nanometers. The power levels, optical power is somewhere between about 10 milliwatts. And the displacements you see are something in the range of 5 to 10 nanometers. Since it's been demonstrated, we are now thinking about applications. Okay, what do you do with this? You can use light and you can push things around. How does this affect how the signals propagate? One area we're looking at is in tuning birefringence. There have been proposals before that if you take waveguides that look like this, they're silicon, they have slots in them, that they have a huge birefringence, meaning light that's polarized this way and light that's polarized this way propagate at very different speeds. So I thought, okay, cool. We have something that looks like a waveguide with a slot in it. And so now we have a force that moves it, so we should be able to change the birefringence, and by quite a bit. So that's shown here. If we consider a two-beam structure that's suspended, the mode that's polarized this way and this way have quite different properties. They propagate at different speeds. And we can calculate dispersion relationships, so we can calculate exactly what the characteristics of those modes are to figure out frequency versus wave vector and figure out the speeds and the phase index, which is characteristic of it. I'm going to skip a few slides here. So what we do then is we consider what happens if you put the pump light in. You'll get a force. They'll deform. And now, as you go along the waveguide, you get a different birefringence, where again, birefringence is a reflection of the difference in how one polarization propagates and the other polarization. And so for a given strong pump signal, we go and we calculate what the force is using the Maxwell stress tensor method, and then we do finite, that'll come next. So we calculate what the forces are. I'm going to skip the details in the interest of time. Then we use finite element simulations to figure out the deformations. So this is showing the displacement of the waveguide as a function of position along the waveguide. You see them deforming. Because they've deformed then, this leads to this birefringence effect. We map out what that birefringence is as a function of position along the waveguide. And we can calculate total phase shifts in the light. The conclusion that we found in this work is that if you have one of these structures for very reasonable powers and realistic geometry, you can convert linearly polarized light to circularly polarized light using this effect, and you can do it in a tunable way. So as you adjust the pump power, you adjust the phase shift, and you can go from linear to circular. We're continuing this work and thinking about other applications that go along with this optical signal processing idea, meaning you use a pump light to control motion, and then some other weaker light signal propagates differently and has, for example, tunable birefringence, effective nonlinearities, and effects like optical bistability. And we're looking at these basic effects and then possible applications to do polarization selective delays, dispersion compensation, and a version of optical logic, such as gates. And this is my student Maggie, who's working in that area. In the last 2 minutes, I'll show you another area that we're working in. I've mentioned several times this idea of photonic circuits. We are trying to figure out ways of making them highly tunable. This is based on work I did as a postdoc. My collaborators, this was first author here was June Pan from Stanford, made these devices. So photonic crystal, you have light going through a waveguide and it can couple into microcavities. And we were able to show that one way of tuning this structure is that you take a laser and you aim it right at a microcavity. Locally, the cavity looks different. So if you remember way back to the beginning of this talk, we said any kind of local change to a resonator, it shifts the resonance. This is one example. You shine light, you get a lot of free carriers right nearby, the index changes and things shift. So we were able to use a laser then to do shift our resonance around we move the laser spot, and we see a shift in the resonance of a few nanometers. We were also able to take a structure where you had two cavities that were initially different, and then take a laser and make those two cavities go together. Here, this is a transmission dip. So you scan wavelength, you see transmission features, and we can bring the resonances together. This here is showing that you can make the resonances cross. So if this is one resonance position, you make the other one move through. My student Eric is currently working, has been working now to get started in the clean room here to adapt our fabrication process to our local capabilities to make photonic crystals. I'm afraid this is not our picture, this is still the previous work. And we're looking at the general idea of how you can use now tunability in order to do things like erase cavities. In other words, make the light not see the cavity, and change spectral response of the devices. And for this, we've been getting a lot of help from Raymond and O'Brien's group, because they've done a lot of these structures here in our clean room and know a lot of the details of the fabrication here. We're also looking eventually at things like reconfigurable splitters, making the light switch from going one way to the other by reconfiguring the circuits. This is my group. I have 3 students from AE, and then I had a new student join in the summer from the physics department, Camilo. And I just want to thank or point out funding sources. So I am now funded by Career Award and an Army Research Young Investigator Award. I also got some money internally through USC. And in the previous groups I can't claim any credit for these, but I can thank the people. We got money from DARPA, DOD, and NSF. My previous advisor had a Packard, which was very nice. He got lots of money from that to pay me. And these are some of my collaborators on the related work from postdoc and grad school, as well as some projects done either during grad school or postdoc. Okay, I think that's it.
Do we have questions for Michelle?
Is bending the light on your trajectory?
Yeah, so you can bend. You can definitely bend.
Can you cloak objects?
Okay. So bending, for example, is easy. You make holes here, and then you make holes here, and then the light goes like that. Okay, so bends are easy. And that's actually, back in the early days of photonic crystals, that was one of the features people were really excited about, is that if you have a fiber optic cable and you bend it too sharply, the light leaks out at the corner. Whereas with these structures, you can make very tight bends with a lot lower loss. Cloaking is also a very popular area of research. There have been all sorts of proposals for cloaks. The general idea is that you can make something where if you have an object, the light comes up to your object, and instead of bouncing off, it bends around it and goes past. And so if you're over there, you don't see the reflected signal, and so you don't see the object. And there's lots of work in this area. And I haven't worked on it myself directly. One of the major limitations with cloaks right now is that they only work at single frequencies. So you don't actually hide objects. You only hide objects if the person looking at you is just looking at a single frequency. But it's a kind of interesting area.
I put only the clay on the cloak, but now Michelle will be cloaking us, so that's a great thing. Any questions to Michelle? If not, let's thank Michelle. Thank you, Michelle.
Can I turn it off somehow?
Don't worry about it.
Don't worry
He's
about
gonna
it.
take care of it.
No.
Very nice.